Hello everyone, Professor Dustin here, and this video is going to be a solution to the whiteboard jumping to a boat. So recall what this whiteboard is all about. We've got somebody who's jumping down to a boat in this orientation. There's an angle here which is 20 degrees, and we know what the speed is right before they hit the boat. And we know what the mass of the person is and the mass of the boat is. First question, what is the momentum of the person? Expressed as a vector just before they land. And then what speed and direction does the boat and person travel after they land? So figuring out what the momentum of the person is, and then doing the conservation of momentum to determine what happens when the boat and the person collide. So recall, the reason you know this is a conservation of momentum problem is two objects are interacting. Two objects are exchanging momentum. Therefore, it's a conservation of momentum problem. Okay, so let's see what we have to do to solve this problem. So first I'm just going to go ahead and name things. M person and M boat. This angle I'm going to call theta, and this speed I'm going to call v person. So for question A, I need to figure out what the momentum of the person is, which is expressed as a vector with x and y components just before they land. So I need to know what my x and y components are going to be. Simplest one I can think of is just stick an xy coordinate system right here. And that's good because the boat is only going to be moving in the x direction. Okay, the person is going to have both x and y components, but the boat is going to have only x components, so that's why I think that is a good option. So what I need to do is I need to figure out what the initial momentum of the person is in the x direction and the initial momentum of the person in the y direction. Momentum is m times v, in this case the person, so mp times vp. But of course this is just the x direction, and there's no, the mass is a scalar, there's no x or y directions for the mass, but the velocity here does indeed have components in the x and y direction. So if this is just the x direction, this velocity needs to be just the x direction. Same deal with the y direction, mass of the person times v person in the y direction. So now I need to figure out what those two components are, which I can do just by going over to my triangle. Actually, let me redraw the triangle so it's pretty clear. That's my vector velocity of the person. That's my y direction. That's my x direction. So then it's pretty clear that that is my vpy, and that is my vpx. And I have an angle in the middle too. So based on a little triangle, we can tell that vpx will be the sine of that angle times vp, and vpy will be the cosine of that angle times vp. To be really careful, we need to see that vpx, this is in the positive x direction, so it gets a positive sign, but vpy is actually in the negative direction, so we need to make sure that we make that thing negative. So there are my two components in the x and y directions, and if I plug in numbers, I get that in the x direction, the momentum is about 233 kilogram meters squared per second, and in the y direction is about minus 641 kilogram meters per second. Sorry, kilogram meters, not meters squared. Cool, so that's my answer for part A, the momentum of the person in the x and y directions. For part B, the person is going to land on the boat, and then together the boat and the person are going to move away with some new speed. This is a conservation of momentum problem. Of course, momentum conservation happens in both x and y directions separately. But since we're only concerned with how the boat is moving, I think that we'll be able to only do the x direction at the beginning. So let's start with just trying to calculate the change in momentum in the x direction, and hopefully that will be enough to get us to our answer. So that means that I need the final momentum in the x direction and the initial momentum in the x direction. Let's do the final momentum first. The final momentum, the boat and the person are going to be stuck together, so they're going to have a common mass, m person plus m boat, and they're going to have a common velocity, which I'm going to call vf. So maybe over here I should have written vf equals question mark to be the unknown final velocity of the boat and the person. Initially, The boat is not moving, so it doesn't contribute to the momentum, but the person is, and this person's momentum is therefore just going to be, the total momentum is just going to be what the person's momentum is, so I should just have that in there. You can replace it with the number, but of course I'm going to use symbols as much as possible, so it should be that thing. Okay, great, so now I can take those two things, put them into this expression, and hopefully be able to solve for the unknown. And indeed, we can see that we know everything in this expression except for the final velocity. So move this thing over, divide by the total mass, and that will tell you what the final velocity is. That's the answer as an equation. If I go over to my calculator and plug it in, I get just about 0.45 meters per second. And that makes a fair amount of sense. Okay, the person is moving pretty quickly at 10 meters a second, but they're not moving in the x direction. They're moving in both the x and y direction, so not all of their momentum will be pushing the boat in the x direction. And further, the boat is really heavy, right? So the boat and the person will certainly be slower than the person moving by themselves. Okay, so let's get part C in here, part C and D in here now. So part C says, if the interaction between the person's legs and the boat took a time of 5 seconds, what was the magnitude of the force they felt during that time? So what we need to remember is the relationship between the momentum imparted on the system and how much force that system felt. And that formula is, the force is delta P over delta T. Now, there are a couple ways of going about to do this, but most students, I think, see this word magnitude and then start getting freaked out. So let's first try to deal with how the magnitude comes into this expression. This, again, because delta P has both x and y components, the force also has x and y components. And so if we're going to try to calculate what the magnitude is, it basically means that we need to do something about the Pythagorean theorem and the x and y components. Well, that we can write in the following way. We can write the magnitude of the force will simply be the magnitude of the change in momentum divided by the change in time. And the magnitude of the change in momentum, we can write that as the Pythagorean theorem, using the Pythagorean theorem. So that's just going to be delta px squared plus delta py squared over delta t. So here is a place where we need to be really careful because we've written delta px and delta py. Over here we use delta px is 0 and delta py is 0. But actually these p's are different. This is the total momentum of the entire system. Remember, momentum is only conserved if you're talking about the total system. The individual pieces of the system don't satisfy this delta p equals 0. And that's what we're talking about. We're talking about this delta p is of the person. So why don't I just label that P, 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 to make sure we're talking about the change in momentum of the person and not of the entire system. Okay, but now we know a lot of this stuff, so we should be able to calculate what the change in momentum of the person was in the x and y directions separately. Okay, so in the x direction, we want to do px final minus px initial. I'm dropping some indices, but just be aware I should probably write xfp and xip, but this is of the person. The final momentum of the person is the mass of the person times the final speed that the boat and the person are moving with together. We know that, we calculated that, it's right there. We want to subtract off the initial, that's mp times vxp, the velocity in the x direction of the person. That is right here. We didn't calculate that explicitly, but it's vp sine theta. So let me just put that in there, actually. And so let's just go ahead and calculate that. If I put that into my calculator, I get about minus 204 kilogram meters per second. So does that make sense? So that means that the initial momentum of the person is greater than the final momentum of the person. And that makes sense because if they have some momentum and they land on the boat, they're going to give some momentum to the boat, so they're going to lose some momentum. And actually that's what the person feels. They feel momentum towards them when they land on the boat. That's what the force of your legs is doing. Okay, so let's also calculate in the y direction. That's py final minus py initial, again of the person. Well, this isn't so bad because the the final momentum of the person in the y direction is 0, because once the person lands on the boat, they're in the boat. Their momentum didn't go in the any further in the y direction. Of course, that's kind of an assumption because we're assuming the boat doesn't go into the water because the person landed on it, but it's a pretty fair assumption. So first thing we're going to do is get 0 for that, and then subtract out the initial momentum of the person, which is MP. And then I should write v person in the y direction. But now we have to be very careful, because actually that VP in the y direction, that's where the negative comes in. So this VP cosine theta should be minus VP cosine theta, because that velocity is actually in the negative direction. So let me be really careful and actually write that in explicitly, minus VP times cosine theta. Put that into my calculator, and I get 641, of course, right? Because 641 was the momentum of the person, and there's no momentum of the person in the y direction at the end. So that's just 641, and now it's positive because those two negative signs cancel each other. Cool. So to get the final answer, all we need to do is take this, put it in right there, take this, put it in right there, square root, divide by delta t, and we can get what the magnitude of the force is. If I do that into my calculator, I get about 1346. And that answer is now in newtons. The reason I know it's in newtons is because I was really careful about keeping everything else in SI unit, and the SI unit of force is newtons. So now I can answer part D. If your legs can sustain a force of about 10,000 newtons without breaking, did this person break their legs? Of course, you can see what I was thinking here. Oh my god, this person's jumping into a boat. I just made this problem randomly up. I don't know if I've ever done this. Would this person's legs break? So I found out that that's about how much force your legs can take. But actually, this force is significantly below that. So, no, your legs would not break. Cool. So the upshot of this problem, although it's lengthy and sort of detailed, is basically centered around this conservation of momentum. This conservation of momentum is the entire system, of which there are two objects, person and boat. And if the entire system is considered, then the change of momentum is 0. The other key thing is that we have a conservation of momentum in both the x and the y directions. Now, we didn't necessarily have to use the y direction here because this is the entire system's y, we didn't use it. But we had to use the x direction to get the conservation of momentum to figure out how this thing was interacting. And again, the reason we know that momentum was the way to do this problem is because we had two objects and they were interacting with each other, and that means conservation of momentum. Okay, great. Hope that made sense. Thanks for watching. I'll see you shortly.